Okay, what we want to do here is we want to download and install Miniconda and add just the minimal amount of modules that are necessary to do some signal processing. So I was looking for Anaconda, minimal install, and then got to Miniconda, and I think what we're going to do is download the latest link here, so Miniconda 3 Windows 64-bit. So let's take that one. So as you can see, this is relatively short. I actually downloaded before Anaconda. That is almost 1 gigabyte. This one is only 73.2 megabytes. And now we can go ahead and we can actually double click on that to start the installation. We need to agree to the end user license agreement. We install it just for ourselves. And this is the place where it will go, Miniconda 3. And it will use about 400 megabytes of data. The full-fledged version of Anaconda uses something like more like 4.5 or 7 or so gigabytes. We want to create start menu shortcuts, but we do not add it to the path environment, and we do not register Miniconda 3 as the default Python. Okay, so it's setting up the package cache, which just contains enough to get started and to have the Conda manager so that we can then add additional components as we need them. Okay, I'm going to stop it here so that we don't have to wait for this to finish. It did actually finish fairly quickly. So here is the screen that we got, and now we click next, and we're gonna get started with Conda. I don't know if we need the welcome to Anaconda, so I'm gonna uncheck that. So we basically have to go to our menu selection here, and then we go to probably Miniconda. Let's see where this whole thing ended up. Here it is. And I think we're just going to run the Anaconda prompt. Let's try that. Okay, so that's basically a baseline, a terminal command line, and we have to take a look what we can do now. So here are some of the things that we want to do now that we are in the Conda environment. First of all, we want to update Conda, so we do Conda and then update Conda, like this. And that shows us the packages that will get updated. So it's basically an update from the time when the binaries were put on the internet, and from the time and the time that we were downloading it now. So we proceed with that, and it's going to download those different things. It's going to implement those, and there we go. So now the next thing is we can take a look at what we actually got in that Miniconda version. So we do Conda list. And here are the packages that we have. So just taking a quick look here, there are some certificates, there is content trust and so on. This is needed so that when we communicate with the database, the Conda database, that there's not going to be any middleman putting in some malicious programs. Then There is, let's see, OpenSSL, that's another one to add some security layer when you communicate over the internet. There is Python here, so we have Python 3.11.4, so that's the basic version of Python. And that's about it. So we could, if we wanted to, I guess we could type Python here and see whether Python is coming up, and indeed 3.11.4 is coming up, so we can do something simple. Let's say we make x is equal to 3 plus 27, or let's say 29, that's a little bit more complicated. And then we can do a print of x. Okay, so that's there. Now we are interested in things like using NumPy and making graphs with Matplotlib and so on, so I can check whether it finds it, but most likely it will not, so I can do an import NumPy as NP. So NumPy is basically a numerical package that makes that you can make arrays with and so on. It's somewhat similar to MATLAB in terms of having arrays and matrices and so on. Okay, so it does not find that, so we actually do a quit out of this. Okay, it wants to have parentheses. And then we go and we actually, well, there are now actually two things we could do. Conda is working in environments. We can actually set up a new environment. And in fact, let's look at what the environment is. So the idea of the environments is that you basically install packages and things within a confined environment so that it's not going to affect other things that you have already on your computer. So you might have different versions of Python, for example, different versions then of the modules that come with a particular version of Python and so on. And so you keep those separate from each other. So if we look here at the environments that we currently have, then we should just see the base environment. That's all we have right now. And so what we want to do is we actually want to create a new environment, and then we're going to download some packages into that. Okay, so we go and we make conda create. And then and test. And so we're going to call it test. And as like a test environment. So we create this. Okay, and so there is the location where that is stored. And then we want to activate that conda activate test environment. Okay, so it is not happy here with what we were doing, so I think I'm going to say yes to that. Let's see what it does. Okay, so it tells us that to activate it, we do conda activate test environment, and then if we want to go into another environment, then we have to deactivate it explicitly again. So let's see in which environment that we are right now. Conda envs. Okay, so I don't know why I don't like that. Oh, it's info. Yeah, and it's conda info. Now we got that right. So we are still in the base environment, but we have created the test environment. And so now we can do conda activate test environment. And now we can see that it actually says there in front test environment, so we are within that environment. And so now we can do a conda list to see what's in that environment. Okay, and so you can see that we basically have nothing in here. And so now we're going to add things to the environment. So I forget what the command is, so I will stop here quickly. Okay, so the first thing we actually have to do here is we have to install Python. Python is not here because we could have used any of different versions of Python. So what we will do is we do conda install Python, and that will install the latest version of Python. If we would want to have a particular version, we could do that. We could, for example, say Python equal to 3.9 to install the version 3.9 of Python. But we want to do the most recent one, and so we are running this. Okay, so it will install those packages. That might take a minute, so maybe I will stop things. Well, maybe it's actually not too bad. Yeah, it was pretty quick. And so now we can do a conda list again. You can see that we have Python in here now. But we don't have NumPy, we don't have matplotlib and so on, so we're going to install those now. It's possible to use either the conda install, or you can install it using pip, which is a Python package installer. So let's try pip here for the NumPy. Pip install NumPy. So that is for the numerical packages. So that downloads what is known as wheels and then installs those wheels. Okay, so it was successful installing that. Let's just for the fun of it try a conda install matplotlib. So that is for making graphs. So it's collecting the data for that. It has to download all those things. Here you can see it downloads actually things in parallel channels to speed things up. It seems to be pretty efficient. And we can see that it's probably going to be done pretty soon. Okay, there's a couple more hidden, which maybe are still working. The whole package that allows us to make graphs of different kinds is fairly complex. And so you can see that it actually was downloading more for the matplotlib package than it was for just Python, the basic version of Python itself. Okay, and so now we still have to get SciPy. So pip install SciPy. SciPy is useful for a number of things, like for example filter design and so on, which is not built into NumPy itself. Okay, so we have that installed as well. So we also want to install Jupyter so that we can use Jupyter Notebooks, and there are a number of different options for doing that. What we are going to do is we're going to use a split installation of the Jupyter Notebook, which puts the kernel inside that environment, the test environment that we have been creating, and puts essentially the main portion that's used for editing and so on into the base environment. So what we're going to do is we're going to do a conda Jupyter, or actually IPy kernel. So that's the kernel that's used for Python. So that we do in the environment that we just created. And here are the packages that it installs for that. So that should be done. So we can list once more what's here. So we do conda list. And you will see pretty impressive list of things here. You can see that we have SciPy. Here you can also see a note here that we downloaded that using pip rather than the conda environment, and probably something similar we will have for NumPy. Let's see where NumPy is. No, it doesn't make a difference here, but we have NumPy, we have Matplotlib, and we have SciPy, which is the things that we wanted to have, and Jupyter should probably be in here so as well. There's IPython, there's Jupyter Client, Jupyter Core, so that's all good. So now we're going to deactivate this environment and go back into the base environment. So we do conda deactivate, back in the base environment, and then we do a conda install nb conda kernels. So that actually will allow us to use more than just the Python kernel. We can use an R kernel or Julia or Java or things like that. Okay, so here are the packages that will be installed. Okay, so that is done. So now we should be able to go in here and just type Jupyter Notebook. And then it should appear in the browser. Okay, so here we go. You can see all the things that are actually available. It basically just shows the directory that we have on that computer. And now we can go and make new here, and then it tells us the different environments that we could choose, and if you would add later a kernel for R, for the language R, or other things like that, that would show up in here. So we have the Conda environment, test environment, so that's the one that we want to use. So we click on that, and then we make a little example. So let's say we're going to do exponential signals. So what I'm doing here is a markdown cell. So I'm going to change that to markdown. So that's something that where I just type comments. I'm not typing actual Python code in here. And so I'm going to write here, and you can use HTML to write things here. So example code to visualize exponential signals. Okay, and then in order to execute the cell, you type Shift Enter like this, and that finishes that cell and starts the next one. So let's see what I want to do here. I'm going to use an example so that I have been trying before. So what we need to do is we need to import some of the packages that we want to use. So we want to import NumPy as NP, and we want to import matplotlib as PLT. Okay, so those are the two things we want to use here, and NP is just a shortcut for NumPy, and PLT is a shortcut for matplotlib. It actually should be matplotlib.pyplot. Okay, so now we import those two from the environment that we are working in, and then we say we're going to make a time axis. Okay, tt equal to np.linspace. And we're going to do, say, from -1 up to 4, and let's make maybe 200 points in that range. It's a command that's actually similar to the command you would use in MATLAB to just make a couple of points along which you're going to evaluate something later. Okay, then I'm going to make an A and an alpha. Zero for the amplitude, and the alpha, I'm going to make it 0.2. That's going to be the rate of decay of that exponential that you want to plot. And then I make x, let's call it xt, because we do it along the lines of that tt. That's going to be a times np.exp. So to use the exponential function, you have to go into the library that actually, or into the module that has that, and it's NumPy, where it's inside. Basic Python does not know about the exponential function. Okay, and then we do minus alpha times tt. And we do that. That should do it. That should compute that xt. So let's enter that. So it's again Shift Enter in order to run it, and then we want to plot it. So we do a plt dot figure. Let's call it figure 3, and then plt dot plot tt comma xt, and we are going to make it in blue, for example. So we do dash blue like this, and maybe we want to have a grid, plt dot grid like this, and then that should actually give us a plot of that exponential. We can change that. We can change, for example, the 0.2 into a 1.2, and that would be an increasing exponential. You know, it's still decreasing because of the minus that we have in front. I would have to make it into a plus to make it increasing. So the 1.2 just actually makes it decrease faster. So if I want to increase the whole thing, then I would have to make, for example, that 0.2 into a minus 0.2 for the alpha. Okay, see that it's actually increasing, an increasing exponential. So we're going to leave it at this 0.2. What you usually also want to do is, if you have a plot, is you want to give it a title and you want to label the axis. So let's do that here. So plt.title, decreasing exponential, and you can use tag commands in here. So I can use alpha equal to 0.2, and then I can do a plt dot y label. So here we can write that this is x of t, and let's see, I have to finish that here, and then plt.x label. So here I can do time t, and that's basically time in seconds. Should be inside the quotes like this, and that should actually label that graph. So you can see it gives that alpha here, for which it's using tech or LaTeX, and then here it's t in seconds, and here is the x of t. So that's a nicely labeled graph. Okay, we can also actually do three-dimensional things. So let's go back and add a little bit something to what we need to import. So this is an additional part of the matplotlib to make it three-dimensional. So we're going to do from MPL toolkits import mplot 3D, like this. And then we're going to do here a new alpha and beta. So let's call it alpha 2. And in fact, we're needing two things here, both an alpha and a beta. So we're going to make an alpha 2, beta 2. We're doing a a complex exponential now. In fact, let's maybe write that here. Insert cell above. And so we're going to make a markdown cell. So what we're going to compute now is a complex exponential. Let's make this as a little subtitle here. And what we're computing is x, let's do that in LaTeX. So x of t is going to be equal to the e, let's make an amplitude as well, a times e to the, actually just single brackets will probably do. It's going to be e to the c alpha plus j beta and then times t. Okay, so we do that like this. Then times t. Looks. Okay, so the alpha, that's basically the damping factor, that's the real part in the exponent, and the j beta, the beta is the imaginary part, and that will actually make a frequency. So this will generate an exponential that oscillates. So it's basically an oscillation with a particular frequency that's determined by beta, and alpha determines the envelope of how that is decreasing. Okay, so we have alpha 2, beta 2. Let's make the a as well. I'm going to make this equal to 1. Let's choose 0.7 for alpha. Let's do 2 times np.pi. So this np.pi, that's how you enter the constant pi, 3.1415, etc. And we could specify a frequency as well. We're just using a frequency of 1 here implicitly by just writing 2 times npi.pi. And then we make another time axis. So let's actually make the a also an a2, so to distinguish it from the one we had before. And then let's make a tt2, a time axis for this, to be equal to np.linspace. And this time we want to start at 0 for the purpose of what we want to show. And we go up to 4 and we make another 200 points. And then we're going to create s, complex variable s being equal to minus alpha plus j beta. Okay, so in Python you have to actually write it as 1j times beta. J could be a variable, and 1j is sufficiently distinct so that it actually realizes that this is the square root of minus 1. Okay, so notice we made it into minus alpha plus 1j beta, so we have a 0.7 for alpha, and by making it minus alpha, we're going to have a minus 0.7, so it's going to be a decreasing exponential. And then we can compute x2t as being equal to np.exp of s times tt. Okay, so that's an easy way to write this by defining s first, and it should actually be s2 and tt2. So S2 is basically the combination of alpha 2 and beta 2. Okay, so now we can do two different things in terms of the display. Okay, so that should be alpha 2 and beta 2. Like this. Okay, so we can make a graph of the real part and the imaginary part separately. So we do figure actually, and let's say we're going to make this figure 7, and then we do a plt.subplot 211, and then we plot the real part, so plt.plot tt2, and then np.real of the x2t. x2t is now a complex valued quantity, and so we pick out the real part here. Let's do this in blue again, and let's do a grid. And let's do a plt.y label of real part of x of t. Okay, I'm just going to call it x of t, even though we call it x2, just to avoid using the same variables for two different things. Okay, I can do a title as well, plt.title, and I can write here complex exponential. And then I do plt.subplot 212, and I'm going to plot the imaginary part, actually I can just take things from up here and copy them over, and then just do some changes. Okay, so it's going to be subplot 212, and I'm going to take the imaginary part of that xt, and I'm going to draw that in red. And then I'm going to write here the imaginary part, and I don't need a title here. What I want to do here is an X label. And I want to write that this is t, and that's going to be in seconds again. Okay, so let's see how that is rendering. Okay, so you can see this here. I don't know why it was writing here text 0.50 and so on. I may have missed something, but at any rate you can see that we do get this, basically this attenuated cosine wave in the real part and the attenuated sine wave in the imaginary part, and the shape by which it goes down, that's determined by the alpha, and the oscillation here, the period of the oscillation, is determined by beta. Okay, now in order to visualize things, it's sometimes useful to make a three-dimensional plot. Okay, so let's try to do this. So we're going to make a new figure. Let's call it figure 11. And we make that plt.figure. So the language, the semantics here are a little bit different when we do the three-dimensional plot from when we did the two-dimensional one. Okay, so just figure 11. and we do an add subplot, and then we do a projection equal to 3D. So in order to find those commands, you basically go to the internet and you just Google those kind of things. It's not something that I know by heart. I'm just looking it up whenever I need it, and then when I have an example, I usually copy it over from other examples. So let's do fig11.plot. And we want to plot TT2, then np.zeros of x2t.size. Okay, so that creates an array of zeros that has the same size as the x of t that we want to display here. And then an np.zeros of x2t.size. So we have this actually twice in here. And we're going to make this into a dashed black line. And maybe we're going to make this with a line width (7). So what this is actually going to be is it's going to show us a straight line, basically the baseline, like the horizontal line that's in here. That's why we put zeros in here, and we have now a 3D projection, so we need altogether 3 coordinates that we input. So we do this along the time axis, and then we have zeros for the real value, the complex value, the amplitude. That's just to give us a baseline. And then we do fig11 plot tt2 again, and then we do np.real of x2t. So we're plotting here the real part in one of the coordinates, and then we do another np.zeros of x2t.size in the other dimension. And so we show basically the projection onto the real part of the 3-dimensional graph, and we do this with a dotted blue line. And then we do a similar thing here. In fact, I'm just going to copy this over now. Okay, so now we're going to take this part and put it here to the end. And we're making this the imaginary part. So that's going to be the projection onto the imaginary subplot of this 3-dimensional plot. And then we're going to do the actual 3-dimensional plot. So the reason why I do this in this particular order is that I want the last, what's showing up best is going to be the last plot statement that I'm doing. Okay, so the plots are basically plotted on top of each other. And my main thing that I want to see is the last one. The other ones are basically auxiliary plots that give me an idea of how the whole plot is actually made up from the different components. Okay, I'll do a plt.grid, and let's actually make the line width of this main one here a little bit bigger. Oops, be lowercase. So let's make this 1.5. Okay, so now let's see what that's going to do. Okay, so here's the picture that we're getting. So you see here in the middle, you see this black dashed line. So that's the baseline. That's basically where the real part and the imaginary part are 0. And when you look at the plane here in the back, that's basically a plane that shows you in the vertical direction the imaginary part, and in the horizontal direction the real part. In fact, let's label this. Actually, I don't remember how to do the labels for the three-dimensional plots. I will have to look that up. Okay, so here is the syntax that we are supposed to use here. We certainly have a nice picture, but now adding the title and so on. So we do Fig 11 set title, and then we do complex exponential, and we're going to write that we have alpha equal to 0.7, beta equal to 2 pi, then we do figure 11 set x label. That's going to be time seconds. Then Fig 11 set y label, and that's going to be the real part of x of t, and then the c label that is going to be our imaginary part. Okay, so now we have a nicely labeled graph. Let's make this a little bit bigger here. So that we get to see it. So one of the things that you notice is that the z label here is actually out of the picture, so we can try to plt.tight layout sometimes helps to get it better displayed. It doesn't actually help in this particular case. So that can be a problem, that sometimes the labeling goes off. It's probably possible by some means to show that up, but we will leave it at that for now. But what you are seeing here is, again, the black line here, that's at 0 on the z-axis and 0 on the y-axis, a straight line coming out, and then the projection to the horizontal plane here at the bottom, which is the real part of x of t. So that's the blue dotted line here. So that's corresponding to the blue that we have up here in this picture. And then we have the red dotted line that is now plotted orthogonal to the blue one, which is the imaginary part. So that's projected basically onto the plane that's parallel to the back plane here. And that would be that red curve here. And then, because we show it in 3 dimensions, we are actually rotating around. It's basically a rotating phasor, and the rate of decrease of that rotating phasor, which is alpha, is actually making that spiral that comes out here smaller and smaller, and essentially you could draw a line along here, something like this, and that would show you the e to the minus alpha times t. So this is a quick way of loading Python to your computer using Miniconda, making an environment in which you can work, and then starting a Jupyter Notebook and making a few simple graphs in that notebook.